Dear APT community, my name is Markus Kühbach. I'm a postdoc at Max-Planck-Institut für Eisenforschung and also a member of the APT TC Committee. And today it's really my pleasure to present you my ideas about how we as a community could become even stronger in aligning our data with the fair data stewardship principles and which consequences and ideas this might provoke for software development. I'm going to start with my perception that many of us in the community feel that APT software could serve us much better. So we need to invest our time wisely, and that is exactly why we need to use productive tools. And software development and FAIR is one such tool. The key statement that I want to make today is that APT software development should be a community effort. Some of you would argue we've done so in the past. I agree, but we could have improved much stronger in terms of avoid re-implementing the wheel. Focus on specific tools, on our specific expertise, and not try to cover everything. So what are the fair data stewardship principles? And why the heck should I care? The fair data stewardship principle in fact state 4 very somewhat abstract ideas that need to be made concrete by implementation and living by a certain community. In our case, I think our community, the APT. Data should be findable, data should be accessible, data should be interoperable, and data should be reproducible, i.e. repurposable for a different task, completely different to what you might have thought your data set might be useful for. So people should be able to find where a data set is, should be able to understand what the story behind that data set is, with as many details as possible. And if you ever want to train a machine to do some machine learning on your data, then you better train the machine and you better inject the metadata such that the machine has the same wisdom as you have on your dataset. But by the end of the day, if a machine is ever to analyze a certain dataset, it needs to understand the data format. And ideally, we as a community want to support and want to be able to parse content from such data. And therefore, I think the only alternative are open data formats. So I want to quickly summarize the status quo on workflows and metadata in ATOM and FIM, so related techniques. We know all that ATOM is essentially a combination of workflows: specimen preparation, measurement, data post-processing or analysis of the data, publication, and then curation of the publication. And I think it's important that we not only focus on the measurement side, only on the data post-processing side, but by the end of the day, that we take into account that all this is coupled into a large workflow with individual pieces, and ideally all of these should be fair. However, if you look in reality at the moment, there is a plethora of tools that we use and a plethora of approaches how we store information with respect to something which by the end of the day ends up in the same figure in the same paper. With the last slide, I want to answer a little bit on the idea, how can I personally contribute to the ideas I've just mentioned? So development of complementary tools and approaches. And for this purpose, I developed one contribution. And one contribution so far is Paraprobe. This is a set of open source software tools. With scientific computing technology in the background. The idea of the software is quite simple. You define your workflow, and that is essentially, I have a data set, several atom types I want to process, several advanced data analysis techniques I want to execute. On all these data sets, on all these possible combinations, then ideally what we do in computational material science, we do batch processing, of course. Yeah, we would never do this manually. And that unfortunately is not so easy with ATOM, and that's exactly what Paraprobe solves. Yeah? So you define in Python what you want, then Python essentially creates the necessary input files. You take these input files and your data sets, go on a laptop, a workstation, a supercomputer, whatever resources you have available, and then the processing is done in the background using performant hardware, whatever you have there. The benefit is everything is open source, so you can dig into. The second benefit is everything is documented, also the metadata. So I've invested quite some time to document what the metadata are. There's definitely not the last shot on it, and I would be very happy to discuss this with you. As a community in particular. And yes, this is the idea in a nutshell. Yeah. So open workflows which use all CPU cores, whether you use a laptop, whether you use available resources, whether you have a supercomputer. And if you have 1,000 CPUs, you want to use the 1,000 CPUs. If you have 100 GPUs, you want to use the 100 GPUs for your task. Yeah, many people can do that in many scientific communities, and that should be also possible in atom probe tomography. And that's why I invested time into this. With that, thank you very much for your interest, and I'm very happy to discuss with you on all sorts of aspects that you've raised also in your talks. Thank you very much. Okay, other questions?
I had a quick question. Before you run your job basically on the supercomputer, how do you know what you want?
You essentially define what you do beforehand. So the tool is rather meant to process combinations of batch processing, combinations of multiple data sets. So essentially for explorative analysis, and you define this beforehand using a set of Python classes. So essentially you write a Python script for which there are tutorials online, and then you create the necessary input files. So this is all hidden in front of the user, such that people have not to wrangle about with text files and so. And then you take a text file, run on a supercomputer or on your laptop or workstation. And at the moment we are working on integrating this into Anaconda, such that people can just download and run it locally. But that's essentially the idea.
That's great. Sounds excellent. Thanks, Markus.
I have a question for Markus.
Sure.
What are your in and your out points for data? Because so far I've only seen sort of the things that have been floating around in Atom Probe, EPOS, and whatnot. But what would be your in and out points?
So my in and out point is essentially, I say one task, one tool. So if you, for instance, make a reconstruction, you go in with your file, whatever it is, APT, EPOS, or POS. That's the input. You do the processing and you get an output. That's a file. And then typically what the next, if you want then do analysis on that, you have the next tool parsing from that process file. So essentially you haggle through your analysis, guided through a set of files which are all open and metadata documenting. There's a little bit the trade-off to make between making it performant, on the other hand, handle large data sets. Of course, there are certain analysis combinations for which it would be smarter to keep everything in main memory, substantially faster. But essentially in the sense that you typically handle only 2 billion points at most, typically in Atom Probe. This for cluster or so workstations is not so much an issue IO-wise. So typically that's why I say you start, you hand data over via files, and if you look into the if I look into the data, how much time typically the IO takes of this compromise, I have to say, then it's in the order of 1 or 2 persons. So that's typically negligible. Yeah. But yes, one task, one tool. So you hand in the result and you pass it to the next stage. And that gives you the flexibility.
You can pull it out at any point.
Exactly. And it's also documenting each step. So also the metadata in the HDF file are documented, so you know exactly what you have done. And that, of course, gives you the flexibility to then parse together the pieces that you want, and also essentially gives the flexibility, if you have other tools, whether it's Python, whether it's MATLAB, to inject code from something else.
So you're using HDF5 to pass it on?
I'm using HDF5, exactly.